Now, there's a great way, remembering way back in Unit 1, of visualizing a difference between two samples coming from different populations. Remember our comparative box plots. So if we take a random sample from men and women, and then we plot their box plots, we can start to see when there are big differences between the two samples, right? So in this case, I actually did that. I randomly sampled from that population data for men and women, and I plotted two of their box plots. In this case, you can see pretty clearly that there's going to be a difference in the height distributions here. So we would expect at the population level, even based on this sample, we would expect at the population level there's probably a difference. However, we really do have to be careful because this is one sample and it's a small little snapshot of what's going on at the population level. There's always a catch. We can be misled. What if we just happen to get an unlucky sample? And this can happen easily enough. The other thing is, how big of a difference do we really need to observe on these comparative box plots in order to say, yes, this is going to be reflective of something significant at the population level? This is not so easy to answer. Let's take a look at some R simulations. So here I have a simulation where essentially I'm starting with two populations that have exactly the same mean. This is important to note. What I'm going to do is collect random samples, two random samples, and I'm going to plot their box plots, right? Sample 1 versus sample 2. The purpose of this visualization is to sort of give you the sense that if you're just working off of sample data, which is what we're going to display here, you can very easily be tricked into thinking that there's a difference in the population when there definitely isn't. I'm telling you ahead of time, these are selecting from the same population, so population with the same mean. So let's click through a couple of different samples here. Here's our first sample. It looks like the blue versus the red, they do seem to be very different. Does that mean they're coming from two different populations? No, they're not. In fact, I'm telling you ahead of time these were sampled from the same population, right? They have the same mean. Let's take a look at another one. These look a little less different. These maybe you'd think are kind of the same. But notice that just by grabbing a couple of random samples here, there's a lot of variation in the box plots you could potentially end up with. Each time I hit the get the new sample, this is potentially data that you would be grabbing by taking a random sample from the population. Right here, they end up looking very, very different, right? Blue sample versus red sample look very different. But that doesn't mean they're coming from different populations. Because again, I'm telling you, these were both sampled from the same population. So you have to be careful when you're just looking at visualizations of sample data. Even though the comparative box plot allows you to kind of spot if there are differences, it's not going to be perfect. And in fact, you can sample two things from the same population and get very different looking box plots for them. So that's why we really need to be careful. And that's motivation for why you would really want to have a hypothesis test, something a little bit more rigorous that will tell you whether or not on the population level, the population means are in fact different between those two populations you're considering. Let's consider one more simulation. In this case, I actually allow, in using these sliders, you can control where the population means actually fall. And I'm assuming they're both normally distributed in this case. And what happens is you can choose your own sampling size, however you want to pick this. And each time you sample from the population, what it gives you is the sample mean from the first population, which I believe is the blue one, and the sample mean from the second population, which I believe is the red one. And again, this sort of purpley color is indicating that one histogram is overlapping the other. The other thing it considers is the difference between the two values that were computed. Okay? So when you have very different population means, right, 105 versus 98, as you sample from the population, more often than not, the difference in your sample means, right, or the difference between the sample means that you get here, how far would you have to walk from this score to this score? More often than not, this difference in sample means ends up being quite large. But what I want to point out is not always. There are some samples that lead to not too much of a difference. What if you're the research team that just so happens to be unlucky enough to collect this pair of samples from the two populations? You may be under the impression that, oh, these populations don't have different means because look at the sample means I got. So we have to account for this random sampling error that could occur. But again, more often than not, the difference between the means between the sample means, I should say, is quite large when you have population means that are very different. Now, just playing devil's advocate, if you have two populations with the same mean, you can do the same thing. And it's still possible to get some values, like for example, this one. You get some unlucky samples where the sample means appear to be quite different. We have a difference in sample means here of a -9, right? But, more often than not, they tend to be pretty small. You tend to get sample means that are very similar. Now, obviously, this variation improves as you increase your sample size. So if I increase the sample size of up to 62, you can see that my difference in sample means isn't quite as variable as it was before. But every once in a while, you can end up with kind of a unlucky pairing of samples that ends up in having what appears to be a significant difference in the sample means, even though we know ahead of time, according to these parameters, that the population means are the same. So what I'm trying to say with these simulations is that in either case, whether you knew ahead of time, and again, we never know this, but whether you know the populations have the same mean or different means, when you look at just sample data, you have to be careful because you could get some unlucky samples. So what we do with a hypothesis test is we try to account for this sampling error, for this variation that comes from only looking at part of the population data, and try to make it a little bit more rigorous and protect against these types of mistakes. Okay, so let's recap. Here we are. We have these populations, heights for men, heights for women. We took a random sample. We have box plots that are different, which makes us suspect maybe something is going on at the population level based on this sample level snippet. But how can we be sure? The question is, how different do these box plots have to be for the samples in order to kind of lift this up to a claim about something at the population? And in fact, we don't even focus on box plots. We focus on the sample means for the men and the women individually. How different must the sample means be to conclude that the population means are different, right? This is statistics. What can we say about our sample that reflects something happening in the population, and how can we make that rigorous? That's what we're trying to do here. So here's our main idea. We're going to collect a sample from each population. X bar sub 1 is going to be the sample from the sample mean from the first population. X bar sub 2 will be the sample mean from the second population. And if we operate under the assumption, the null hypothesis, that the population means for these two different things are the same, then basically the sampling distribution of this difference of sample means will be centered at 0. We have a good R simulation for this, so let's take a quick break and take a look at what happens with this. Okay, back to our usual sampling distribution visualization. Again, the idea here is we can set the means and the populations using these sliders. So I can consider a case where the means are the same or a case where the means are decidedly different. We can change the sample size that we want to work with this slider. And then I can essentially look at or generate, by collecting one sample and then eventually hundreds of samples, I can generate a sampling distribution for the difference of sample means as I take a random sample from the blue, a random sample from the red, compute their means separately, and then look at their difference. Let's start for when the populations are essentially the same. So let's assume population 1 and population 2 both have a mean of 105. Now let's take a look at samples of size maybe 20. If I get one sample, I get something a little bit off of 0, and so you can see I'm slowly building my histogram of the sampling distribution for x1 bar, x2 minus x2 bar. And I collect a couple hundred samples, and I get a nice approximation for what my sampling distribution would look like. Now what I want you to notice is that when the population means are the same, the sampling distribution for x1 bar minus x2 bar is centered at 0. These are the most likely values. They're also close to 0, okay? With some sort of variation. Now, as usual, the amount of variation from that peak decreases as I increase my sample size. right? So I see much less variation away from 0 when I have a sample size of 200 versus a sample size of 43. Now let's take a look at what happens when the population means are different. So now we have a difference between 96 and 105. Let's set a reasonable sample size of maybe 30. I can collect one sample, two samples, and we can see that with the first few samples, the most obvious thing that we can notice going on here is that the difference in the two sample means ends up being moved far away from 0. So if I could do this a couple hundred times, the peak, the most likely value for this sampling distribution, x1 bar minus x2 bar, right, the difference between the two sample means, the peak is moved away from 0 when the population means are different. And so this is the idea. We can fit this nice normal distribution curve here. It ends up actually having a t-distribution, as we'll see in a second. We can fit this nice bell-shaped curve with a probability distribution. And when the population means are different, right, we're more likely to collect a sample difference of means that's far away from 0. And under the null hypothesis that the means are the same, we would expect that sample mean or difference of sample means should be near 0, which will allow us to get p-values that are small. So this is the main idea. All right, so our typical null hypothesis is going to be that the population means are 0, and this will mean that the sampling distribution of x1 bar minus x2 bar will be centered at 0, as we just saw with our R simulation. Now, we can use a sampling distribution of x1 bar minus x2 bar under this null hypothesis assumption to find p-values based on the assumption that the null hypothesis is true. Now, I'm going to talk very quickly about what the sampling distribution actually looks like. It ends up having a t-distribution, but it's a little bit different than what we're used to. We don't have to know any of that because in the end, we're going to be just using a single Excel command to compute these p-values. So this is really more of a theoretical or conceptual idea of what's going on. I want to reflect what we've seen in the one sample tests, but don't worry too much. Don't get too nervous about what I'm about to show you. So basically, the idea is the sampling distribution for the difference of sample means tends to have its peak around the difference in the population means. Now, under the null hypothesis that the means are the same, the peak here ends up being at 0. What's our probability model? What's our standard error or the variation in the sampling distribution? It ends up having a nice t-distribution. And the standard error is this really, really ugly looking formula based on the sample size that you take from group 1 and the sample size that you take from group 2, the sample standard deviations, et cetera, et cetera, et cetera. But again, you don't need to know any of this because it's all going to be taken care of using our Excel command. The main idea here is that in theory, this thing that we take a look at, the difference between the sample mean from population 1 and the sample mean from population 2, essentially has a t-distribution, which allows us to compute p-values. Okay, so what is our Excel command? And let's do some examples finally. One nice benefit of the t.test command is it's going to bypass a lot of the work that we saw with our one sample hypothesis tests. In other words, we're not going to be computing test statistics. We're not even going to be computing sample statistics. We're just going to plug the raw data into our command, indicate what kind of test by using this tails part, and the type is always going to be fixed. Specifically, we'll have two types of null hypotheses, one where the first population has a greater mean, or the first population has a smaller mean. Both of these are going to be one-tailed tests, so we're going to set the tails argument equal to 1. Our last type, a two-tailed test, which claims that the null hypothesis says both populations have equal means, since it's a two-tailed test, we're going to set tails equal to 2. For our class, we're always going to set type equal to 2. All right, so what I want to do now here is go over an Excel example that's going to use this t.test to do a comparative means hypothesis test.